going to move on to the last question, just number 5. We've been given a sketch of this cubic function. We first need to write down the values of x where the graph intersects the x-axis. Alright, so one approach I suppose you could take, if it's intersecting the x-axis, these are 3 points where the y-coordinate is equal to 0. So we could change our y value into 0 and try to solve this equation. Unfortunately, this is beyond our algebraic capabilities. We don't know how to solve cubics. We can solve quadratics by factoring or using the quadratic formula, but not cubics. So I'm going to enter it into the calculator and put it in as a new function. Alright, 4x cubed minus 9x squared minus 12x plus 3. And I'll put it on a regular viewing window, zoom 6. Alright, maybe I should adjust my window so it looks a little bit more like that. I clearly need to be able to see more of the action down here, so I'm going to increase my y min. It's also apparent I don't need to see such a big X or such a small x, so I'm going to decrease my x max and x min in my window. So let's bring the x max and the x min down to say -4 or something. I'm sure that will still be enough. And we'll bring the min down to -30. See how that looks. Nice. Okay. Right, so we need to find the 3 x-intercepts, don't we? So that's the zeros, so I'll look for the zeros. My left bound, let's start with this leftmost 0. A point that's safely to the left of it is -2. A point that's safely to the right of it is, say, -0.5, and I'm going to guess that it occurs at -1 in, not quite, it happens at -1.099. If we rounded that to 3 significant figures, we'd end up having -1.10. Our next 0, our x-intercept, occurs, so a left bound of say -0.5 and then a right bound of say 1, and I'm going to guess it occurs right at 0. Actually occurs at 0.218 if I round to 3 significant figures. And my last 0, so my left bound is 3, my right bound is 4, and I'm going to guess that they intersect at 3.1, and it's actually 3.13. Okay. Alright, let's move on then to part B, where we need to find the derivative. So f prime of x will differentiate the 4x cubed. The 4 hangs out in front, and the x cubed becomes 3x squared. The -9 hangs out in front, and the x squared becomes 2x. We know that the derivative of -12x is simply -12, and the 3, the derivative of any constant, is 0, so it disappears. And I'll simplify this to 12x squared minus 18x minus 12. Okay? Now we need to find the value of the local maximum. So we know that a maximum occurs when we have a stationary point, and a stationary point means that your derivative is equal to 0. Let me just check I copied my derivative correctly. Yes, it looks good. Alright, so I need to solve that equation. One way I could do that, I suppose, would be to put that into the calculator. In fact, I could divide the entire equation through by 6, couldn't I? So I divide it all through by 6, I get 0 equals 2x squared minus 3x minus 2. I think this is going to factor nicely into 2x and a 1x. And so if I put a minus 2, oh, that won't work. Let's try this. Minus 2 plus 1. There we go. If I multiply that out, I'll end up getting my original expression. So either 2x plus 1 is equal to 0, which means that x is equal to negative 1/2, or x minus 2 is equal to 0, which means that x is equal to 2. So these are the two stationary points. I should now classify these stationary points as maxes or mins. So there's my negative 1/2, and there's my 2. And I'm going to substitute in a test value from each of these three regions. So I'll put a negative 1 into my derivative. So if I put a negative 1 into my derivative, I'm going to end up with, let's see, 12 times negative 1 squared minus 18 times negative 1 minus 12. That's going to give me a negative value. If I put in, wait, does it? 12? No, it doesn't. It gives me a positive value, excuse me. If I put in a number between negative 1/2 and 2, maybe like 0, then I'm going to end up with a negative value. And if I put in a number in this region like 3, I'm going to end up with a positive value. And so you can see that your graph is going to be increasing where it's positive. Here's the stationary point where it's 0. It's decreasing in this region. Here's the stationary point where it's 0, and it's increasing in this region. And that, of course, does look like the cubic that we got on the original graph. So clearly we've got our maximum happening when we are at negative 1/2. So it says find the value of the local maximum. The value is the y-coordinate. That's what the word value means. So we need to find the y-coordinate when x is equal to negative 1/2. So let's substitute negative 1/2 back into the original function. A quick way of doing that, because I've already entered it here, would be to say second calc, and let's find out what the value is of the function. So value when x is equal to negative 1/2. And we're told that we get a y value of 6.25. So that's your answer, 6.25. We could have also solved this problem by just looking for the maximum coordinate. So if we say second calc on our original graph and did the maximum coordinate, left bound, move it a little bit to the left, and then we'll move it a little bit to the right, and then we'll put it right on top, and hit enter for the guess. And I hope that you can interpret this. This means obviously that x is equal to negative 0.5, and the y value, as we already found, is 6.25. Okay? Alright, part D. Let P be the point where the graph intersects the y-axis. Well, intersect the y-axis is code for y-intercept, which means that x is equal to 0. So if we substitute x equals 0, and remember we're substituting into the original function because we're looking for the y-coordinate, so x equals 0, and what's the corresponding value of y? If we substitute 0 into the original function, you'll see that the first three terms will all disappear, and I'll be left with just a 3. Another way we could have done this is by finding out what is the value of y when x is equal to 0, and it will tell you that y is equal to 3. Part E, find the gradient of the curve at P. That means find the slope at point P. Well, we know that the coordinates are 0, 3, so x equals 0, right, is the x-coordinate. And we know that we can find gradient because gradient, or slope, is the same thing as the derivative, right? These mean the same thing. So the gradient or the slope at x equals 0 is going to be the derivative at x equals 0. So let's substitute 0 into the derivative, and we'll get 12 times 0 minus 18 times 0, and we're left with negative 12. So m equals negative 12. Okay? Lastly, we need to find the equation of L in the form y equals mx plus c. So clearly your slope is negative 12. So let's substitute in a known point like this coordinate 0, 3. So here's my y-coordinate, here's my x-coordinate. This disappears and we discover that c equals 3. And therefore your function is y equals negative 12x plus 3. And there's the equation of the line L. Okay? Just a quick picture of that if you wanted to imagine what this looks like. When we were at 0, 3, you can see that point. It's indicated right now on the calculator, and you can imagine if I drew the slope of the tangent along that line, or if you like I can show you here, it would clearly be a negative. It's decreasing, so it's going to be a negative line. Turns out that that line will intersect the y-axis at, of course, 3, because that is a point on the curve. 0, 3 is a point on the curve, so clearly that is the y-intercept. Let's move on to the last portion, part G. There is a second point Q at which the tangent is parallel to L. Parallel to L, that is code for same slope as line L. And if you remember the slope of line L, which was the tangent, this was the one which had a slope of negative 12, wasn't it? So the parallel line must also have a slope of negative 12. So there we go, we've done part G. Part H, we need to calculate the x-coordinate of Q. So you remember that our derivative, just go back to our derivative for a moment, 12x squared minus 18x minus 12. That's our derivative. And we're interested in finding out, where is this derivative, this gradient expression? I know that the value of the slope is equal to negative 12. Right, so because I know the gradient, let's substitute the gradient in for f prime of x. And now I'll find out what are the values of x at which the gradient is equal to negative 12. Some of you have the bad habit of, when you've been given the gradient, you substitute it in for your x value. No, that's not correct. You haven't been given the x value, you've been given the gradient, so substitute the gradient into your derivative expression. Right? Not for the x value in the derivative, but for the f prime of x itself. That is your slope, that's your gradient. Okay, so I need to solve this equation. So let me start by bringing the negative 12 over to the right-hand side. It becomes a positive 12. And in fact, with the negative 12, they will cancel, right? So if I just add 12 to both sides, they cancel. In here, I can divide the entire thing through by 6. And now I can do a little factoring, and there's a common factor of x, and I'm left with 2x minus 3. So either x is equal to 0, or x is equal to positive 3 over 2, right? If 2x minus 3 equals 0, I'm going to get this one. Now, I already knew about this one, right? I already knew that when x was equal to 0, I would have a gradient of negative 12. I found this point out already. I knew my gradient was negative 12 already at x equals 0. So what I was really interested in finding out was, where is the other place where the gradient is equal to negative 12? And that's going to be the x-coordinate of Q. Okay? So x equals, yeah, that's going to be the x-coordinate of Q. And we're done on this review. So good luck preparing for this very important test.